Hi, my name is Ken Casey with Texas A&M AgriLife Research in Amarillo, where I work on gaseous emissions from animal agriculture. Today I'm going to talk about some painful experience that I've gained over the last 4 years in trying to make measurements of greenhouse gases from feed yard pens, basically. And there's nothing marvellous about what I've learned or what I'm going to present here, but it just represents how all the little steps that are involved in adapting a technique from one area of science to another. And they're all important in obtaining good results. As presented by other speakers here this morning, including Dr. Cole, the emissions inventory for feed yards and for beef is dominated by enteric emissions. The emissions inventory for the feedlot manure management system is dominated by methane in mass terms. But in carbon dioxide equivalent terms, it's dominated by nitrous oxide because of the greater warming potential. There's been relatively little research on methane and nitrous oxide from these management systems, particularly under the climatic conditions that exist for the major US cattle feeding areas. As an example, the IPC workbook for nitrous oxide basically just has a simple emissions factor of 2% of the excreted nitrogen is going to turn into nitrous oxide. No temperature dependence, no impact of climate, of moisture content, etc. So basically says we don't know very much about it. So our overall objective and goal in this is to try and understand better what produces these greenhouse gases at cattle feed yards. Magnitude, spatial and temporal variation, etc. And with the idea of being able to do a better job of inventorying it and to be able to model it such that you might be able to identify mitigation practices in the future. But to do any of that, you have to be able to measure it to start with. Different approaches to doing that are small-scale chamber-type techniques or large-scale area integration techniques. The chamber techniques, widely used in soil science, established protocols. However, they measure a relatively small area, and if your area is spatially and or temporally variable, they're somewhat limiting. If you don't do it very well, your measurement system can influence the results you get. Chamber environment can measure the temperature and pressure in your chamber environment, can enhance or suppress emissions. How you install the chambers could enhance the emissions. The base itself can alter the environment that you're measuring. They're not real-time measurements. You tend to collect samples, take them away and analyse them. Sometimes later you get your result. There are automated chamber systems, more mechanically complex, often hooked to very expensive instrumentation to do the real-time analysis. Area integrating techniques. A number of people have used open path measurements using FTIRs to measure emissions from feed yards. So you're integrating that spatial variation. If you measure for long enough, you pick up the temporal variation. They're challenging to operate under feed yard type environments for any length of period of time. Eddy covariance is another technique that's possible. You may infringe upon some of the assumptions that you need to make it work in a feed yard, like things that move around and obstructions. And you also need a pretty expensive instrumentation system to make it fast enough and make it work. So as a first step, we decided to go with chambers. And that's what they look like in practice. A steel ring that's driven into the manure surface, cap that's fitted over that. A seal that's turned up to join the two of them together, gas accumulates in it, you sample it over a period of time and get an increase in the flux, increase in the concentration, which you can mathematically turn into into a measured flux. Most of the time in Texas, that's what your feed yard looks like. Very powdery on the surface, compacted below that. Very occasionally, it gets a little wetter. So what are the challenges in doing that? These non-flow through, non-steady state chambers have been well researched, they're well documented in the literature. Hutchinson and Mosier are very well founded in the literature in terms of defining how they're used. How do you use those to sample from feed yard surfaces, and what are the issues? What we decided, we would choose one time in the day, noon. We would use 10 chambers within a feed yard pen. Try and integrate some of that spatial variability to get a better average. We would take measurements daily over 5 days. We would collect 4 gas samples in our 30-minute deployment system period, and we would use a quadratic calculation process. Why do we choose 10 chambers? It's quite a bit of spatial variation within the pen. Wet areas, dry areas, areas close to the feed bunks, close to the water points, etc. Try and get a better handle on what the average might be, and also be able to look at what that variation is. A compromise between labour and resource availability. It takes a finite period of time to sample each of these chambers. You tie up resources in terms of building them, installing them, and analysing them. One operator can manage 10 chambers. He can't manage more than 10 chambers. We use a recently emptied pen. We obviously would like to measure what's happening while the animals are there. That's difficult. The animals are going to disturb the bases out of curiosity, amongst other things, and or they're going to be potentially injured if they step on the steel base. And practically you cannot guard the bases for any length of time while the animals are present. So we build our chambers out of an 8-inch PVC pipe cap, scepter in the top to allow gas removal, a balance tube to balance the pressure inside, steel pipe base, lower edge sharpened to help us drive it into the manure pack. They're installed 3 to 4 inches driven into the pack. There's a rubber skirt that's rolled up to seal the cap onto the base. When I started, I contacted various other researchers in the soils community and talked to them about how they did it and what sort of equipment they used. These photographs come from Rod Venturia with ARS, who's very experienced in the area, and represent a system that's used in cropping. A larger area, metal pan, insulated, metal bases, a seal there, when clamped onto the base, samples deployed. We would have trouble installing something that large into the feedlot pack. So therefore we chose a slightly smaller model. Installation of the bases, the manure pack is quite dense and particularly under dry conditions, very hard to penetrate. We couldn't drive that light metal base in without basically destroying the light metal base. One of the problems is that when you have a hard surface underneath and you drive something into it, you fracture it. Therefore, you enhance whatever flux rate you might have. So you're trying to measure what's happening in situ without influencing what's going on. The GraceNet protocol calls for waiting at least 24 hours before you take measurements. We trialled this in some of the experimental Feedyard pens and confirmed that when we drove our base in, we ended up with an enhanced flux rate. We decided that we would wait at least 48 hours before taking measurements, and in fitting in with getting access to a pen and running for a reasonable period of time, we tend to take possession of the pen on a Friday, establish the bases on Friday afternoon, start making measurements on Monday. So there's a period where the animals are not present and we get past any enhancement in the emission rate. This is how Rod's crew install his bases in the field, put a piece of plywood over them, gently tap them in with a hammer. We tried that, it didn't work. We started out with an asphalt tamper, and after we broke several of those, we built our own. And the base here is three layers of half-inch plate welded together. Now that works pretty efficiently. You need a fair bit of upper body strength, and you don't need to go to the gym after you've spent a day in the field. The problem is, it does require a fair bit of upper body strength and control to be able to drive the bases effectively and not promote fracturing. We've now moved on to using a 30-pound slide hammer. That is not much easier, but it is more consistent, and we are able to drive the bases with less fracturing. When I first bought this system, we deployed our 10 chambers in a field near the office and conducted some training events. And we did that twice. I never had any problem with the system. The first time I took it to the field, there is a 2-foot extension there so that it means you stand upright while you're driving them in. That's 1-inch solid steel. In the first 2 chambers, I bent it. Now we have 1 1/4 inch hardened steel extension. I haven't managed to bend that just yet. So our bases are installed into the pack. We did evaluate other techniques that we'd found that other people used. Manure or sand piled around the chamber to create a seal. Didn't work for us in Texas sort of conditions where the manure is dry and the wind blows a lot. We tried a plastic skirt attached to the cap and weighted down. Once again, didn't give us as good a seal as we got if we used the base driven into the pack. The maximum, the highest flux we measured was with the base driven into the pack. There are a number of different calculation procedures in the literature. A lot of people use linear regression. Some people use quadratic. Some people use the Hutchinson-Mosier approach, and there are other more complicated approaches that are more data intensive and processing required. You can see some of that. Anyway, for carbon dioxide, this is, I'm going to show 2 slides. One shows the emissions measured on Monday from this particular chamber, and we can see that we've got a pretty good linear fit on for carbon dioxide, methane and nitrous oxide. By the end of the week, we've had a change in temperature, we've had a rainfall event, and we're not looking very linear anymore. So we chose to start our analysis by assuming that we're going to fit a quadratic to it. Sometimes it works out that linear is equally as good, but we just decide that we're going to use the quadratic approach that used our data effectively and suited the sort of data that we were getting. We've developed some software that we can evaluate different models and look at the effect of taking out one point out of our 4 points that we collect. This is a typical layout we use of our 10 chambers, 2 rows, 5 chambers in each row. You can actually see the back of the pen in this photograph. Sometimes the dust is such that you can't see the end of the row. So graphically, pens are about 200 feet by 80 feet. Normally there'd be about 100 animals in that pen. Gas sample collection. We started out with these vials here, a screw top vial supplied by the company we bought our GC from, Varian. We could never make them work. They would work okay, but we were really happy that we were getting them absolutely evacuated and they maintained a seal. We moved on to using these exotainer vials, which we're much happier with. These ones have one septa in them, these have 2 septa. We tend to use these, allow us a greater storage time, and we reuse the caps 3 times. When they're used with just 1 septa, we tend to cycle the cap, replace the caps each time. You need to prepare the vials. We use an automated rig that evacuates, fills with helium twice, and then evacuates again to make sure that your vial has nothing in it before you start. Has a fair impact on the quality of data you get out. We use an automated auto sampler on a GC that does methane, carbon dioxide, and nitrous in one go. Having got your sample, what's the calibration on your instrument? What range are you calibrating over? I do a fair bit of analysis for cropping and rangeland scientists. Carbon dioxide, methane, nitrous, over 1,000 measurements in a cropping system. You'd say that my CO2 is 1,500. I might calibrate over 5,000 parts per million. Methane is 3, perhaps 5. Nitrous 1, perhaps 5. This is what I get from manure. Maximum 55,000. 700, 400 parts per million nitrous. And what we started out with, surveyed the literature, talked to people, what range do you calibrate over? So we'll bump it up a bit. It was nothing like what we needed. So this is our second set of calibration standards. We were running 5 levels. We now run 7 levels. As we go on, we get a better handle on what the range of concentrations we experience. Of course, most of those samples are low-level samples, but the high-level ones you need to be able to accurately measure them as well. So if you're thinking about getting into this area, and you think the guy down the corridor who does analysis for soils, who's already got his GC set up, is a good person to go and talk to about getting your samples run, make sure he knows what his calibration range is and what happens when he's outside his calibration range. Because the electron capture detector that you're using to measure nitrous oxide is not linear. Our lab running cropping samples may not even know what their linear range is. They may not be running 5 or 7 samples, 7 calibration levels. They may be running 1. Our system is linear out to about 10 parts per million. We analyse using a low range calibration curve, and anything that exceeds that that 10 parts per million, we reprocess the chromatogram with a different calibration curve. Trying to fit something in the GC's software just does not work. Despite the fact that it'll tell you its R squared is 0.999, the results are not good. We know we've evaluated our minimum detection level and the minimum flux we can get. So, results. Interesting things you can see. Start out. It's dry. The wind's blowing. Overnight it rains. Suddenly your nitrous oxide shoots up right off the scale. By the end of the week, it's back down to almost background. If you measure multiple times during the day, you can see the response to change of temperature. So what have I talked about? There are unique issues in measuring greenhouse gases from waste. A small, insignificant variation from your established protocol can immediately turn your results into manure. You need a good measurement strategy and equipment. You need to understand your sample collection and storage requirements. You need to understand the minimum detection level of your system. You need to have thought about your flux calculation methodology. You're going to get temporally variable results. You're going to see large influences of rainfall events and a fast response to changing microclimate. And once you've got your data and you still think it's no good, there are large challenges in analysing it. Thank you.